Hi, my name is Malik Magdan Ismail, and first of all, let me apologize for not being able to have a physical presence at the conference due to visa issues. Um, so I'm going to try to present the talk via a video. This work is joint work with Kshitish Hegde, and the title of our work is that the intrinsic scale of networks is small. So the main goal is to define what it means for the scale of the network to be, for example, 10 nodes. And what we're going to talk about is how to do that, and then we're going to study the intrinsic scale of a variety of networks. So, moving towards a definition, what we can ask is at what scale, and hopefully small scale, so at what small scale does a network identify itself? And the natural question here is from what? And the natural answer here is from another network. So, one might like to say that, the scale of a particular network is small because, look, if I look at a small part of this network, then it looks very different from, let's say, the Wikipedia network. There's a problem with this definition / methodology, which is that, why should the scale of one network depend on what's going on in another network? There's no reason for that, and it's a little bit unnatural. So what we are looking for is a definition of the intrinsic scale of a network. And this should have nothing to do with what's going on in the rest of the world. Okay, so this is our main contribution, is to sort of define and investigate this notion of an intrinsic scale in a network. And of course, we're going to show lots of interesting results with real networks. The punchline is that when you look at real networks, it's no surprise that we find that the intrinsic scale is around 7 to 20 vertices. What does this mean? What this means is that the identity, the structure in real networks reveals itself at very tiny scales, handful of vertices. So, if you look at, let's say, a Facebook network around the order of 10 node subgraphs, you can start to see the emergence of the Facebook network. And that's interesting because in that regime, sort of parameters like power law scaling and clustering coefficients, they don't really make sense at the 10 node scale. Nevertheless, we can still identify that there is structure there. So, how do we define the structure in the network? And this is intimately related to what happens to a network as you perturb it. Okay, so what we see at the bottom of this slide is a graph, N0, think of it as a social network, and at each step, so N0 to N1, N1 to N2, N2 to N3, N3 to N4, at each step what we're doing is we take an edge and randomly perturb it. And sort of the mechanics of perturbing an edge are not so important. Essentially, we take a pair of edges and rewire randomly, and now we obtain a perturbation of the graph at each step. Okay, and as we perform more and more random perturbations, so for example, when we go from N0 to N1, you see that N1 still looks a little bit like N0. And when we go from N1 to N2, N2 looks a little bit like N1, but has started to lose its resemblance to N0, and so on. As you make more perturbations at N4, we now at N4 have sort of what appears to be a random network when you compare it with N0, the original network with lots of structure. Okay, so what we take away from this slide is that you can take a network and you can randomly perturb it. Okay, and this has nothing to do with any other network. Okay, and as you randomly perturb a network, it starts losing its structure. How can we use this observation. Okay. Well, the basic idea is that if a network has structure at a small scale, okay, and then you perturb the network, you get a perturbed network, and you can look at this perturbed network at a small scale. So let's say by small scale we mean a 10-node subgraph. So you take a 10-node subgraph of your original network, and you take a 10-node subgraph of your perturbed network. Okay. The perturbed network is supposed to look random, so this 10-node subgraph is supposed to look random. So if the original network was also more or less random, then these two 10-node subgraphs, one from the original network and one from the perturbed network, will look very similar. Okay. So what does it mean if these two 10-node subgraphs from these two networks look very different? What it means is that the original 10-node subgraph does not look very random, i.e., it has a lot of structure. Okay. And so, you know, the disappearance of structure from a network as you perturb it will be revealed by the ability to distinguish small subgraphs on the randomly perturbed network versus small subgraphs on the original network. Okay. So this leads us to define the lift in some sense. So you take a network, you perturb it, let's say delta perturbations, okay, and now you look at subgraphs of size kappa, and the ability you have to distinguish these two subgraphs of size kappa, okay, we will call the lift delta of kappa, and the lift, which is a function of kappa and of delta. Okay, so kappa is the size of the graph, and delta is the amount you perturbed. So if you perturb a graph, look at a subgraph of size kappa. If you can distinguish it from a kappa size subgraph of the original network with very high accuracy, let's say 90% accuracy, you've got a huge lift of 40% from random, and this means that the original network had a lot of structure. If, on the other hand, you cannot distinguish these two subgraphs of size kappa, it means that the original network was looking kind of random, and basically there's no structure in the network at the size of kappa. Okay, so this leads us to this definition of the lift, which depends on how much you perturb the network delta and what size subgraphs you're looking at. Okay. Now we can define the intrinsic scale. The intrinsic scale is the size of the subgraph you have to look at so that when you perturb a graph, you can distinguish the perturbed subgraph from the original subgraph. Okay, so let me repeat that. Supposing that if you look at a 10-node subgraph of an original graph, now you perturb the graph and you get a 10-node subgraph of the randomly perturbed graph, and these two subgraphs look very different, it means that the original graph has structure at the scale of 10 nodes. Structure that's very different from random. Okay. And so what we're looking for is the smallest number of vertices such that you can distinguish the original subgraph of that size from a randomly perturbed subgraph of that size. And at that point, we say that we found the intrinsic structure of the network. Okay. So, intuitively, at the scale of the intrinsic structure, a network has revealed itself, and we can now distinguish it from a random version of itself and presumably also then from other networks. But notice that no other network has entered into the definition of the intrinsic scale. Okay, so here's how we go about estimating the intrinsic scale. Basically, we need to be able to estimate the lift. How distinguishable are two subgraphs? So let's focus on the flowchart on the left. We have two networks. One, the original input network, and two, the network which we have perturbed, which is obtained from the original input network via random edge swaps. Think of it as a random version of the input network, which has the same degrees and lots of similar properties. Now, from both networks, we extract subgraphs. Then we run a deep learning classifier, a convolutional neural network. That's not so important. Okay, so we run a classifier and we ask, what's the accuracy for discriminating between an input network subgraph and the perturbed network subgraph? And if the accuracy is very high, it means that there's a lot of structure. So we can convert that accuracy into a score. The details are not important, but we can get into the details. And for those, I refer you to the paper. So at some level of scale, kappa, and for some number of edge swaps, delta, we can assign a score which says how distinguishable is the subgraph from a random subgraph of that same size. And the more distinguishable, the more structure there is in the network at that scale. Okay, so let me show you some results on lots of data sets. Okay, so what I'm showing here, let's suppose we fix the number of perturbations to a small value, something like 10% of the number of edges. So we're going to randomly pick 10% of the edges and perturb them randomly, keeping all the degrees of all the nodes the same. Okay. At various scales, we can ask, what's this score? What's this lift? How much structure is there, okay, at various scales? And what we're showing is a set of networks. The higher the accuracy on the y-axis, the more the scale at the 10% perturbation level. And you can see that the networks cluster into, roughly speaking, 3 groups. Okay, the top group is the group that has lost its structure very quickly, just for 10% of perturbations. And what you'll observe, the top 2 curves are, the Facebook curve and the Al-Qaeda curve. What this means is that not only is there a lot of structure, okay, in those networks, but that structure disappears very quickly with a small number of perturbations, 10% of perturbations. Okay, then if you focus in on, let's say, a scale of 24, you see at around an accuracy of 60%, you have a bunch of networks. What are these networks? The Goala network, the mouse network, the human network, the yeast network. So biological networks. Okay, these biological networks, even at the scale of 64, but let's focus at the scale of 24. At the scale of 24, these biological networks are not very distinguishable from a 10% perturbed version of the network, which means that they look more or less the same. In other words, we haven't been able to tease out any structure yet, so they're sort of robust to these perturbations. And then there's the middle group, which contains networks like DBLP, the web, the road network, and so on and so forth, that are intermediate. So they have some structure at the 24 vertex scale for a mere 10% perturbation in the original network. Roughly speaking, we can conclude that the social networks are sort of fragile, the biological networks are robust, and then there's this intermediate information networks which seem to be, in between. Okay. So I mentioned this notion of robustness, and what I've linked that to is how quickly does the network become distinguishable from its random counterpart, for a small perturbation. How easily is it to distinguish? And we saw that there are these networks which very rapidly lose structure and are very distinguishable even for just 10% of perturbation. And then there are these networks that take a long time to lose structure. In other words, they have maintained their structure. Okay. Here's what happens for a larger perturbation of the network. So we can look at 20% perturbation, 30%, and so on and so forth, up to infinity. So as you add more and more perturbation to the network. And what you can observe here is that as you perturb a network ad infinitum, essentially all the accuracies go up to close to the 90% level. Okay, so what this means is that, in this case, I'm showing you the intrinsic scale of size 16. Okay, and if you allow me to perturb as much as I want, then even at a 16 node scale, a network is distinguishable from a totally random counterpart. Okay, so this suggests that there's structure at the 16 node scale in pretty much all the networks that we have tried in real applications. And this ranges from social networks to information networks to biological networks. So conclusion, the intrinsic scale of almost all networks that we have observed is around 16. And the minimum is around 7, the maximum is around 20. Okay. You will observe that, however, the behavior of these networks for small perturbation is very different. And that's the slide that we saw earlier. For small 10% perturbation, some networks have lost a lot of structure and the score is very high and it's very distinguishable from its random counterpart. And some networks have not lost much structure. So if you look at the small perturbation of a network and how much structure did it lose as measured by the ability to distinguish, we have a notion of robustness. Okay, and some networks are robust and some networks are quite fragile and lose a lot of their structure very quickly. If you look at the large perturbation regime, in other words, we've basically constructed a random network with the same degree distribution. If you look at a large perturbation, we find that almost all networks are distinguishable from their random counterpart. Okay, so this means that for example, at the scale of 16, there's a structure in these networks. But it's harder, depending on the network, it can either be hard or easy to tease out that structure. Okay. So in some sense, we get at the amount of structure in a network by looking at the large perturbations. We get at the rate at which structure can be removed from a network, that the rate at which it disappears, some measure of robustness by looking at small perturbations. Okay. And let me show you on an easier to interpret diagram how the networks behave with respect to this robustness characteristic and this intrinsic scale characteristic. Okay, so here's a scatter plot where on the x-axis is the intrinsic scale, on the y-axis is the robustness, and just recall, intrinsic scale is, at what scale can you distinguish a network from its random counterpart? Okay, and robustness asks, at what level of accuracy can you distinguish between a network and a small perturbation of the network? Okay, so what you observe is there's a general trend. Okay, the robust networks tend to be the biological networks, human, wiki, yeast. The non-robust networks tend to be the social networks, Al-Qaeda, Facebook. And this sort of makes sense that, in these sort of human social networks, you pick your friends very carefully, and, there are probably lots of fine-tuned structure in them. And if you make a small perturbation, it's going to look very different. Okay. Whereas biological networks, perhaps they've evolved to have some kind of robustness, to be able to tolerate errors and so on and so forth. Okay, and in between, on the robustness scale, are the information networks. Okay. When it comes to intrinsic scale, so the scale at which a network reveals itself, no surprise, the road network has a very small intrinsic scale. That's sort of validation that the methodology is working. So if you look at a roughly 7-node subgraph of a road network, you will see the intrinsic scale of this network. You will see the structure in this network. And the intrinsic scale of the biological networks are largest, and intrinsic scale of the information and social networks are somewhere in between. And you will observe this general trend that, larger intrinsic scale leads to more robustness. And there's no surprise there. If you have a larger intrinsic scale, it means that we have to look at a much larger piece of your network in order to identify the network, which also suggests that you're going to need many more perturbations to lose that structure. So you will also be more robust. The interesting counterexample there is the human network, which has a very low intrinsic scale, but is very, very robust. So it has to be able to tolerate, perturbations, but nevertheless, it needs to be able to function at a very fine-tuned scale, and so it has a very low intrinsic scale despite having a high robustness. Okay. And that more or less brings us to the end of this talk. I would just like to summarize the two contributions. The two main contributions are that we have introduced this notion of intrinsic scale and a methodology for evaluating, for computing it on real networks. This methodology does not depend on any other network, so we define the scale of a network intrinsic to the network. And we've validated that we get interesting and sensible results on a variety of real data sets, and we see interesting trends like a intrinsic scale robustness trade-off. There are lots of open questions. Can we construct networks and models that can sort of explain these different kinds of intrinsic scale robustness trade-offs? What kinds of networks have structure at very small scales and yet are very robust? Can knowledge of the intrinsic scale of a network improve well-known clustering, network analysis problems such as clustering, and so on? So how can knowing the intrinsic scale help you with clustering? Well, if you know that the intrinsic scale of a network is 7, it suggests that the cluster sizes that are meaningful in these networks should be of the order of 7, maybe 7 to 20. So it gives you some idea what kinds of cluster sizes you can use to pre-populate algorithms which take as input, a suggested cluster size. And, that's all I have to say. If you have any questions, please feel free to email me, magdan@cs.rpi.edu. Thank you.